Hello everyone, today we'll be going over Griffiths Problem 12.3. For part A, we're asked what's the percent error introduced when you use Galileo's rule instead of Einstein's, with VAB equals 5 miles per hour and VBC equals 60 miles per hour. This is a simple plug and chug of Galileo's rule. Velocity with using Galileo's just gives us 65 miles per hour. Now, Einstein's is a little more complicated, but it's defined by equation 12.3. Note that to keep things simple, after a quick Google search, the speed of light in miles per hour is 6.708 times 10 to the 8 miles per hour. So, after plugging in the values into equation 12.3, we don't get a number that's easy to express. So I left it as a happy face, but using Excel, we can keep it as is. So, to calculate percent error, when we're comparing it to Einstein, it is velocity of AC using Einstein minus velocity of Galileo using Galileo, and velocity using Einstein. And that gives us a percent error of 6.5589 times 10 to the minus 14%. So it is very small. Now, moving on to B. Suppose you could run at half the speed of light down the corridor of a train going 3/4 the speed of light. What would your speed be relative to the ground? So, let's break it down a little bit. The problem saying that we are running at half the speed of light down a corridor of a train. So this is the velocity of A with respect to some moving train. That means VAB is 1/2 c. Then it's saying that the train is going at 3/4 the speed of light. So that is the train of B with respect to C. BBC equals 3/4 c. And we're asked to calculate VAC. We're using Einstein's rule again. I rewrote it for clarity and wrote it again just as a reminder, and I rewrote our values. And from this point forward, it is plug and chug. And at the end of it all, you get 10/11c, which is still less than the speed of light. Moving on to C. We're asked to prove using Einstein's velocity rule that if VAB is less than C and VBC is less than C, then VAC is less than C, and we're asked to interpret the results. So, this is Einstein's rule, and this is the problem we stated again. So, I first started by defining some new values that will help us write this equation in a cleaner way. V1 is equal to VAB over C, V2 is equal to VBC over C, and V3 is equal to VAC over C. So then, when you solve for VAC, VBC, and VAB, VAC is V3 times C, and then VAB is C times V1, and VBC is CV2. After plugging in, we're left with this expression, and I rewrote it just for clarity, and the C squared cancels out, and the C's on both sides cancels out, and we're left with this expression. Our original statement saying VAB was less than C, when you plug in VABC, the C's cancels out, and so now our new statement is V3 is less than 1. So this is what we're asked to check. Now, how do we proceed with this? Well, it's not straightforward. It's already written out here, but maybe I can explain how it's motivated. If we see in the denominator, we have a V1, V2 term. In the numerator, we have a V1 plus V2 term. So it seems like I'm potentially squaring this to get that term. And if I do square this, I can potentially manipulate the fraction into some form where it's 1 plus or minus some terms. Then I can compare whether V3 is less than 1. Having said that, we square both sides. And after squaring both sides, we're left with this term right here. I rewrote it for clarity, and then I rearranged the numbers. I moved this term to the front and moved the other two to the back. So then, the difference between the numerator and the denominator is that I would like to have a 1, and I would like to have a V1 squared plus V2 squared. I can add a 1 as long as I subtract it later, and I can add a V1 squared or V2 squared as long as I subtract it later. And then I still have my original V1 squared plus V2 squared terms on the end. So now I have this part over this part that turns into a nice clean 1, and I'm left with this fraction over here. I rewrote it for clarity, and this isn't quite factorable just yet unless you pull out a minus 1. When you do that, you're left with 1 plus V1 squared times V2 squared minus V1 squared minus v2 squared. And then this is factorable into 1 minus v1 squared times 1 minus v2 squared. And now we can start making comparisons, noting that our denominator goes back to the original 1 plus v1, 2 squared. I had a typo, but I fixed it. Okay, so our v1 is equal to VAB over C, and we're given that VAB less than C, so that forces V1 to be less than 1, and by a similar argument, V2 is less than 1. I rewrote these up here for clarity. Now, since V1 is less than 1, and V1 is squared, this whole term is forced to be less than 1, and it's forced to be positive. Similarly, this term is also less than 1. So I have a term that's less than 1 times a term that's less than 1, so the entire thing has to be less than 1. Now, the denominator is going to be greater than 1. And you might ask, well, what if V1 is positive and what if V2 is negative? Well, we have to go back to the original equation, remembering that this is equal to V3 squared. So, what that means is that this here as a whole has to be positive. Otherwise, we would get imaginary values for V3, and that is not a thing. So, if this term has to be positive, this term overall has to be greater than 0, and for that term to be greater than 0 with the numerator positive, this also has to stay positive. So that is why this term is positive, and if this term is positive, then this term is greater than 1. So having said that, the numerator is less than 1, the denominator is greater than 1, that means this entire term is less than 1, which means that this entire term is less than 1, telling us that our V3 is less than 1. What this tells us is that VAC is less than C. And what this means is that for all velocity less than 1, the fundamental limit is still going to be C. Thank you.